we are discussing about the halides. All reacts with halogen to form the trihalides and the pentahalides. Except nitrogen, all can form pentahalides. They can expand their octates, but nitrogen cannot expand its octate due to the absence of d orbital. So all forms two types of halides, that is trihalides and the pentahalides. So all elements forms trihalides, that is EX3, and pentahalides. And the pentahalides, that is EX5, except nitrogen due to absence of d orbitals. Absence of d orbitals, we used to say that. So due to the absence of d orbitals, we can say that all forms, that is trihalides, will be formed by nitrogen as well as other elements, whereas pentahalides is not formed by the nitrogen, but other elements can form the pentahalides also. So we can say that the covalent character of that is, we'll say that the covalent character of that is mx5 is greater than mx3. All trihalides and the pentahalides of nitrogen is unstable. Because of that repulsion between the lone pairs, and we'll say that it is it cannot form a pentahalides, but the trihalides are unstable because of that is repulsion between the lone pair of nitrogen and the halogens. It is only NF3 because of the maximum extent of overlapping which is stable and it exists. It is stable, you can say. Existence is for all, but the stability is only of NF3. So all halides of nitrogen, we'll say that that is NX3 are unstable except that is NF3, which is stable, except that is NF3, which is stable. Others all are unstable, the trihalides of nitrogen, we used to say that. So in case of nitrogen, NF3 is known to be stable, but BF3, all the trihalides are covalent. So except, we used to say that, except BIF3, all other trihalides and pentahalides, all other, you can say that MX3 and MX5 are, also that they are covalent in nature. If they exist, they are covalent in nature. But BF3 will have the ionic character because of the difference in the electronegativity it is. So that is how we are able to write that, and it will also have some partial covalent character, but it will have more ionic character than the covalent character. So that is how we are able to discuss about the trihalides are. So this is all about the trihalides. We'll write that about these elements. Now we can write that the next is, we can write that the reactivity towards metals. So if we talk about that their reactivity towards metals, we can say that. Then we can say that towards metal, we know that the nitrogen, the phosphorus, they all react with metal to form nitrides, then it is phosphides, like that. So we used to say that all forms binary compound exhibiting -3 oxidation states. All forms binary compounds with -3 oxidation states. -3 oxidation states. So that is the nitrogen form nitrides. So all will have the suffix of "ide." All have the suffix that is "ide." This is the suffix what we have. So nitrogen form nitrides. We say that, for example, we can say that this is lithium nitride, magnesium nitride, Mg3N2, calcium nitride, beryllium nitride, Be2N2, Be3N2, we used to write that. The nitrates I'm talking about. So they all form the nitrates. Boron nitride, aluminum nitride, that is like this. We used to write that. So that is how we write that these are the nitrides are. Similarly, we used to write that the calcium nitride, magnesium nitride, we can write all these nitrates. Ca3N2, we'll write that Ca3P2, the phosphide. Like this we are able to write. That is, then we can write that arsenide, that is Na6AS2, we used to write that. So that is arsenide, Na6AS2, that is arsenide. All these are having -3 oxidation state in this. -3 oxidation states. As I've told you, they are forming that -3 oxidation state. Similarly, we can write that for antimony, that is Zn form, that is Zn3Sb2. We'll write that, and that is antimonide, that is also having -3 oxidation state. Whereas, so as in nitride, we get that phosphide, we get that arsenide, we get that antimonide, and we also get bismuth. So bismuthide, that is Mg3Bi2. So all forms, that is they react with metal to form, that is a binary compound with -3 oxidation state. So in all these, there is a -3 oxidation state of these elements. This shows their non-metallic character of these elements. So that is about that reactivity with metals. We should remember all these. They can form that the sulphides, that is, this is phosphide, calcium phosphide, sodium arsenide, zinc, antimonide, and this is magnesium bismuthide. So we'll write well bismuthide and other names of these elements. Nitrates, so many we have discussed that. We used to write that nitrates. All these on hydrolysis gives their hydroxides and their hydrides. So hydroxides of the metal and the hydrides of that is non-metal. So we get like this, that is the compound is. So on hydrolysis we can write that. On hydrolysis we are going to write that. Suppose I've written that, that is calcium nitrate, Ca3N2, when reacted with water, it will give ammonia plus, we are going to write that, that is calcium hydroxide. We'll write like this and balance the reaction. Whereas we can write that, suppose we are having that Na6As, right, now 2. When treated with water, I'm going to write that it is, we're going to write that it is ASH3 plus, I'm going to write that Na1. So like that, we are going to get that the arsine gas is formed. So like that, we are able to write that. That will be given when we are going to treat that with, with water. So on hydrolysis, they used to give the gases and the base. That is how we are able to write that about the reactivity of, that is, we say that it is towards metal. So that is their reactivity towards metal is. Now we can discuss about the nitrogen. Now if we discuss about the nitrogen, we know that nitrogen is an inert gas. Nitrogen. So nitrogen, we know that how we have to prepare that. So we can discuss about the preparation of nitrogen. The preparation of nitrogen. So we are going to discuss that, how that nitrogen can be prepared. We know that nitrogen can be prepared by many methods. We know that what are the methods for the preparation of nitrogen is by heating with ammonium, that is ammonium dichromate, by heating that ammonium nitrate, ammonium nitrite, we can heat that. Even with the purest form of nitrogen is formed by the azides, that is the barium azide or sodium azides, like that. So that is how we are going to form the nitrogen. Then we can write that the preparation methods, we can write that the first preparation method for that nitrogen we can say is the commercial preparation method. So commercially it is prepared by, that is distillation. Distillation, and that is, first it is liquefied, then it is distillate. So liquefaction and distillation. Liquefaction and distillation from the air sample and distillation from air sample. That is air samples, because air contains the atmosphere contains 78% of nitrogen. The atmosphere contains the 78% of nitrogen. So we require that it is from the air. So the boiling points of, we can write that because the boiling point of N2, that is very low. The boiling point of N2 is 77.2 Kelvin. 77.2 Kelvin, and the O2 is equal to 90 Kelvin. So we can easily distillate, that is the boiling point of oxygen is higher than that of this, so its boiling point is less. It means that we can say that we can easily distillate these two from the difference in boiling point. The difference in boiling point is large, so we can say that they can be easily liquefied as well as they can be distillated. So that is how the commercial preparation is. So commercially it is the cheapest source of nitrogen is air sample, so from the atmosphere. Next is the lab method. We used to say that the laboratory method is, lab method for the preparation is for the nitrogen. It is that when we react, suppose we have to write that the lab method, we will say that when ammonium chloride, suppose we are going to write that ammonium chloride, when it is treated with that is NaOH. So I'll get that when ammonium chloride is reacted with Na, or we can write that it will be better to use, because in this case first we'll get ammonia, then ammonia has to be decomposed. So better to write that we'll take directly that NaNO2. Then if we take NaNO2, we'll get NaCl initially, plus we'll get that N2, plus we'll get that twice of H2O. So in this case we directly get that is the nitrogen gas which will be present in that. Similarly, I can write that as we have written here, but in this case what happens, that the impurities present are, present in this method are, that is nitrogen oxide, and we'll write that the impurities which are present in this method are the nitrogen oxide and HNO3. So NO and HNO3 which can be removed, easily, which can be removed by treating the mixture with, by reacting the mixture with that is we can say that concentrated H2SO4, it will remove the HNO3, H2SO4 for HNO3, and that is K2Cr2O7 for the removal of that is NO. So we can remove these impurities. Or we can say that the nitrogen oxide is also absorbed by ferrous sulphate solution. So we can treat that, we can pass this NO gas in the ferrous sulphate solution. Then also it can be removed from there. So we can remove that impurities like that. Also we can write that the lab method, another method we can write that in the lab method, that is decomposition of ammonium dichromate. So decomposition of ammonium dichromate, when it is heated, then N2 is liberated plus chromium oxide is formed, that is a green solid, plus H2 is formed in the reaction. So we used to write that there is a green solid which is formed, and the nitrogen gas is liberated in this case. So we get that the reaction is like this. So these are the lab method for the preparation of nitrogen gas is. Next we can write that a very pure nitrogen atom. So a very pure nitrogen atom, the very pure we can say nitrogen gas, N2 gas, is prepared from, we can write that the very pure nitrogen gas is prepared by the decomposition of, from the decomposition of sodium and barium azide. So that is from the sodium and barium azide. We can write like that. That is sodium and barium azides are. So if we have barium azide, I'm going to write that like this. The barium azide, we can write that. The barium azide is BaN3 whole twice. We can write that. So when it is decomposed, we are going to write that it will form the nitrogen, that is N2, we can get that N2, and we are going to write that the product, which is the side product which is formed, is the metal plus barium used right now. Or we can write that the sodium azide NaN3, when it is heated, it will form N2 plus we get that sodium. So that is how we are able to get that the very pure form of nitrogen is. So this is how we used to prepare the pure form of nitrogen from the sodium azide and the barium azides are. So this is how we are able to prepare, that is the very pure form of the purest form of nitrogen we get as. So this is about the preparation of nitrogen. Now we can write the properties of nitrogen. So we can write that few properties like that. The properties of nitrogen, we can write that the properties of N2, I am going to write that it is a colorless, odorless gas. So it is a colorless, odorless, inert gas, non-toxic, inert gas, right? It doesn't react easily with oxygen or any other metals or non-metal. It is, it has very low solubility in water. It has very low solubility in water because nitrogen is an inert gas. It doesn't have polarity, so it doesn't dissolve in water. What we say that it reacts at high temperature directly with some of the metals. You can write this as one. It reacts at high temperature directly with some of the metals. So we'll write that directly. We know that we have written the nitrates directly with some of the metals to form nitrates. Metals to form nitrates. We used to say that. So they will give us the nitrates. That is nitrates. So like that we used to say that. For example, we can say that the lithium metal will react with N2 to form lithium nitrate, that is Li3N. The magnesium reacts with right now. So we can write that lithium nitrate, magnesium react with N2 to give you magnesium nitrate, Mg2N3. So I'll write like this, that is twice. That will be 3 by 2. I can write that like this. Similarly, I've written that so many nitrate, you can directly write these reactions of nitrate with the nitrogen and these metals. So we can get that the nitrates of those metals. So these are mostly the nitrates are ionic in nature. Mostly the nitrates are ionic in nature. Due to the difference in the electronegativity, we'll say that are ionic in nature. But few can be the covalent nitrate. Few of them can be the covalent nitrate with the non-metals. But when react with non-metals or react with non-metals, it forms covalent nitrates. Non-metals, it forms covalent compounds. So in that case, it can form the covalent compounds, the nitrogen. So nitrogen with H2 can form ammonia, like that we are talking about. So we can say that what are the reaction of that covalent nitrate, how we get that covalent nitrates are. So we'll write that it is like this. You can write that the reaction with the other non-metals to form the covalent nitrogen compounds. So we can write that if we talk about that, for example, I can write here only. For example, we can say that it is that is N2 plus 3H2. We'll write that 3H2, it will give us that is twice of NH3. The delta H of reaction is exothermic, that is negative. Whereas if we react with the N2, and we can write that N2 plus O2 will react to form, that is twice of NO, and the delta H of reaction is greater than 0. because it required temperature around 2000 Kelvin here. But in this case, the temperature is very less. Reason? Because it is an exothermic reaction. So we can write that in this case, the reaction is carried out at low temperature, whereas in this case, the reaction is carried out at high temperature. And in this case, the nitrogen can have, here we can say that these are the reaction of nitrogen with the non-metals, whereas with the metals. When it reacts with metal, they are ionic hydrides. When it is reacting with the non-metals, it is called that is ionic nitrides, and this will be the covalent nitrides, what we used to say that. But we use the word nitride when we are reacting it with the metals. We used to say that. So we use that name that is like that is the nitride is. So that is how we used to say that nitrides are. Next we can write is what are the uses of nitrogen. So if we write that what is the uses of nitrogen, so it is an inert gas. Inert gas. If it is an inert gas, it is used to provide the inert atmosphere at when it is required. So we used to say that we will say that it is used to generate it is all required to produce the inert atmosphere in the industry. So it is an inert gas, so it is used to generate or provide the inert atmosphere in the industries. Industries. Right? Then we can also say that its main use is the preparation of ammonia. Right? So its main use is the preparation of preparation of ammonia and calcium cyanamide. Preparation of NH3 and the calcium cyanamide. The calcium cyanamide, we can say that. The calcium cyanamide. The main use is the preparation of ammonia, and we say that the calcium cyanamide. And the liquid nitrogen also used as the liquid nitrogen. Nitrogen is also used as, we used to say that, the refrigerant. The refrigerant. It is also used as the refrigerant in right now to preserve biological materials. To preserve the biological materials. Biological materials. Even we can say that because it will preserve the biological material because it generates the inert atmosphere. As we say that in that Lay's chips and all now, they all are having that nitrogen gas inside them because it generates the inert atmosphere, so that biological material, the potatoes, doesn't react with the environment, and so their pH remain balanced, and thus they will not destroy. They will not give us the foul smell, or they will not get destroyed because of that nitrogen gas present in that. So that is about that. We'll say that the nitrogen, and that is what we required about the nitrogen is the preparation, the purest form of nitrogen, how we can prepare that, the laboratory method, how we get that, and that is all about the nitrogen, what we required is. So that is about the nitrogen, what we required in this chapter is. Now we can say that we can discuss that the other compound, we can say that the compound of nitrogen, the compounds of nitrogen we can discuss. The compounds of nitrogen we can discuss. The very first compound is, we can say that the ammonia. Ammonia is one of the important compounds of nitrogen. So ammonia, I'm going to write that. That is NH3 we are going to discuss. So this is one of the important compound of nitrogen is, we know that. So if we discuss that the ammonia is, how we are going to discuss that ammonia, we can say that. That is, we can say it is present in air and soil. It is present in air and soil. Because ammonia in the soil, that is nitrogen fixation, we know that. Soil in small quantities, no doubt, in small quantities. So in small quantities, that is, so, but it is present in ammonia is present in that is soil as well as in air, that is in nitrogen cycle, we know that. So now we can write that its preparation methods. In soil we know that, in soil, the urea which is present, NH2CO, NH2, we used to say that. If we are having that urea, if we heat that urea with water, it will get converted into the ammonium carbonate. So we get that ammonium carbonate. Now this ammonium carbonate, when it is heated, it goes to decomposition, and on decomposition it gives us, that is in equilibrium state, that is we can write like this, in equilibrium state it will give us ammonia plus CO2 plus water, we can write that. So this is how we get that ammonia from the soil, that is present in form of urea. Even we know that when we add urea and water, it will get converted into this, and in presence of sunlight, it decomposes into ammonia. That is how it will present in the soil. So that is how we get that ammonia in the soil is. But we can say that this is one of the methods for the preparation of ammonia, that is in soil and air, how it is formed. That in soil it will be in form of this, that is decomposed from the urea and get converted into the ammonia gas. So it escaped in the atmosphere. Another method what I can write is, that is on a small scale we can prepare like this. On small scale we can prepare the ammonia like this when we are having like this, that is if I am having NH4Cl and if it is treated with, that is the ammonium salt. When it is heated with, that is the base like calcium hydroxide, or with we will say that sodium hydroxide. So I will say that with calcium hydroxide, we'll write that it will get converted into CaCl2. We'll write that plus NH3, we get that, plus we'll write that the water is formed in this reaction. So we get that ammonium chloride, we get water, and we get that it is like this. So that is how we are able to write that the reaction, the formation of ammonia is. Not only this, we can also write that if you are having ammonium sulphate, and if you are having ammonium sulphate, not only with this calcium hydroxide, you can directly use sodium hydroxide also, or calcium hydroxide. So if I add, suppose, sodium hydroxide in this, I'll get that Na2SO4. I'll get that ammonia is liberated in this, and we get that water is also formed like this. So that is how we are going to get that the reaction is. That is how we will write that the small scale ammonia can be prepared by this method. So, but the large scale of preparation is done by Haber process of ammonia. The nitrogen combines directly with hydrogen. So that is called the Haber process for preparation. On large scale, we used to say that is industrial or the commercially how ammonia is prepared. So large scale, that is commercial preparation, we used to say that. So commercial preparation of ammonia. Preparation is done by, is done by Haber process, we used to write that. So the Haber process for the preparation of ammonia, we used to write that in Haber process. Now in Haber process, what we say that is the N2 gas reacts with the hydrogen gas in excess. So if it reacts with hydrogen gas, what we are going to get is, that is NH3 is formed in the reaction. Now I will write that what are the conditions. It is at very high pressure because the volume is going to decrease from 4 volume to 2 volume, and the temperature is also generally high. The reason is the temperature is high is to increase the rate of reaction, even though it is going to be the endothermic reaction. So we used to make that. It is the pressure is 200 atmosphere, and we used to say that is around 700 Kelvin is the temperature. That is 450 degrees centigrade. That is the temperature. And in this case, the catalyst which is used in the reaction is, so the catalyst used are, we used to say that is the iron catalyst, that is, we used to say that Fe2O3 with some amount of, so we say that Fe2O3 with K2O and Al2O3. So with these are the used as catalyst in the reaction with some amount of K2O and Al2O3 to increase the rate. So in this case, to increase the rate, the effectiveness of catalyst, increase the rate of reaction, we used to say that. the rate of, and molybdenum is used as a promoter in the reaction. So MO, that is the molybdenum, is used as a promoter in the reaction. So promoter in the reaction, that is used as a promoter for the reaction, and we get that ammonia is right now we get the ammonia in the reaction. And the delta H of the reaction is also positive, even though we know that we are going to write that because we are increasing the temperature. It is an exothermic reaction. Initially, if we prepare in the laboratory, it is generally an exothermic reaction. So, but we are increasing the temperature, so it becomes endothermic, and we say that the delta H of formation of this is minus 46.1 kilojoules per mole. So that is how, that is the enthalpy of reaction is. The enthalpy of formation of the reaction is. So these are the conditions what are required for that preparation of ammonia by the Haber processes. When the nitrogen in gaseous state is mixed with hydrogen, excess of hydrogen in 1:3 ratio, you can say, then in that case we used to get that the ammonia is formed. Another, we can write that by the cyanide process. We know that by cyanide process we can say that the cyanide process is, we can say that the preparation of ammonia, that is, we can say that by the cyanide process. So actually calcium, that is, we will have that calcium carbide we can prepare, or we can directly take that calcium oxide. So when calcium oxide reacts with carbon, we get that calcium carbide, CaC2. So calcium carbide and carbon monoxide. Let us add nitrogen in this so that we are able to write that calcium cyanamide. We'll get that calcium cyanamide, that is CaCN2, plus that is C is formed, that is called nitrolium. So this nitrolium is formed. Now this calcium cyanamide which is formed, when it reacts with H2O, it will form CaCO3 plus we'll get that ammonia is liberated in the reaction. That is nitrolium fertilizer, we used to say that. So in this case, when calcium cyanamide is hydrolyzed with water, we get that calcium carbonate, and that is a solid which will be remained, and we'll get that ammonia is liberated in the reaction. This carbon can be again used with that is calcium oxide, and it is with nitrogen. So we get that ammonia by that calcium cyanamide process is. So that is how we are able to form that nitrogen. That is how we get that the preparation of nitrogen is from the cyanide process. And that is all what we can discuss about the preparation of ammonia is. So that is how you can write that it is water, that is in gaseous state, or you can heat with water, you can say that. So it should be in form of steam. So when heated with water, we get this. So that is called the cyanide processes. So these are the preparation methods what we required for the preparation of ammonia is. Now we can discuss about the properties of ammonia. Now if we discuss that about the properties of ammonia, we get that the properties of NH3 is the ammonia. We can write that. The properties of ammonia, we can write that it is, we can say that NH3. It is colorless gas with the pungent odor. So we know that it is a colorless gas. Colorless gas with pungent odor. With the pungent odor. Even its melting point and boiling point is very less. Its freezing point is like this. Its freezing point is equal to 198.4 Kelvin. Whereas it's right now we can say that we can write in terms of degree centigrade. Its boiling point is, that is 35 degrees centigrade. Is equal to, we can say that, minus 35 degrees centigrade. So we can write that in Kelvin also, but we'll discuss in degrees centigrade like that. So we can write that its melting points, its boiling point in solid and liquid state, it is a hydrogen bonding. It shows, we can write that, it shows hydrogen bonding, it's bonding in solid as well as liquid state. Bonding in solid as well as in liquid state. In liquid state, you can write like this. So it can right now show hydrogen bonding in solid as well as liquid state. So it can show the hydrogen bonding in solid as well as in the liquid state. So that is the property what we can say that for the ammonia is. Now we can say that it is highly soluble in water. We know that. So we can write that it is highly soluble in water because of the hydrogen bonding. So it is highly soluble in water. Soluble in water due to hydrogen bonding. Water due to H bonding, we can say that hydrogen bonding. And that will be like this. Ammonia with water will give you that that is NH4OH, and NH4OH which is formed will establish an equilibrium of ammonium ion and that is OH negative ion. Because the Kb for this ammonium, that is reaction, is 1.8 10 to the power of minus 5. So that is the Kb for the reaction is. So it is weakly basic, we can say that. Ammonium hydroxide is weakly basic. When ammonia reacts with HCl, it forms ammonium chloride, which is a white dense fumes. So we can say that when ammonia reacts with HCl, reacts with the acids to form. So we can say that, so it reacts with acids to form salts. To form the salts, we can say that. Form salts. So we can write that because it is basic in nature, so it will react with the acids to form the salts. HCl, it forms ammonium chloride, like that we can say that. So salts, that is NH4Cl, we can say that, ammonium sulphate, we can say that, NH4 whole twice SO4, we can write, etc. We can write according to the nature of salt, that is acid used, we are able to write the salts in that case. So we can write that this is about, that is ammonia is. You can write that about the ammonia properties. So it forms like this. So it precipitates. So its aqueous solution gives the precipitate with the certain cations. So we can write that its aqueous solution. Aqueous solution gives the precipitate with the ions. So we can say that these are used for the detection of ions, that is chromium ion, like we can say that Al3 plus, Cr3 plus, you can write that that is Fe plus 3, you can write that Sn plus 2, you can write that it is, we can say that it is zinc plus 2, we can say that Pb plus 2, that is like this, we can say, etc. You can write. So many ions are there. So if you write that suppose having that Al plus 3, when that is treated with ammonium hydroxide, I'll write that with ammonium hydroxide, I'll get that that is the aluminum hydroxide is formed. So aluminum hydroxide is formed, that is gelatinous white PPT. Gelatinous PPT. White PPT we used to say that. White PPT, then we used to write that similarly, I can say that similarly we say that it is chromium hydroxide is a green PPT. Write that FeOH whole thrice is a brown PPT. And I'll say that it is zinc, tin and lead. All forms white PPT. Similarly, we'll write that the zinc hydroxide, PbOH whole twice, and the SnOH whole twice forms the white PPT. So these are the color of the precipitate and the precipitate which are formed on reaction with that is what we say that is ammonium hydroxide is. So these are the reactions of the ammonium hydroxide with different cations to give you the precipitates. So it is used in the detection of certain ions, we can say that. So with the cations and hydrate and even their oxides and their salt solutions. So with this we can say that even it reacts with the salt of these ions. So we can write that it is, we'll write that Al, if you're having aluminium, that is some salt is present in that. So I'll write that aluminium chloride or it is zinc sulphate, or we can write that the salts like this. or FeCl3, or we can write that it is say that zinc sulphate, PbCl2, SnCl2, we can write that CrCl3, like that, etc. Even with the salts, it will give the same reaction. So even with it reacts with the salt of these ions to give the same precipitate, to give same PPT. That is, we can write that. Even the salt will give the same precipitate, not the ions, even the salts or their oxides, we can say. Due to its basic character, that is, we can write that due to its Lewis basic character, it forms the complex with the ions, forms the complex, what we call that it is the complex, or we say that coordination compound with the ions such as we can write that is zinc ion, the cadmium ion, the silver ion, Au, that is we can write that copper, nickel, right, Ni plus 2, we can write that. Then we can write that it is cobalt. We have written that cobalt also. Yes, it is cobalt plus 2, etc. We can write that. So it can form a complex with so many ions when it reacts. So due to its basic character, it will donate its electron pair in the empty orbital of these ions and it forms a complex with that. So these are the ions which are going to form the complex with it. So that is how we can write that its properties are. So we can write that its thermal decomposition. We can write that its thermal decomposition. So thermal decomposition, right? When we write its thermal decomposition, so we'll write that it will divide in certain parts. We can say that when the anions present are, so when anions present are, we say that it is Cl negative ion, sulphate ion, like that, etc. Then ammonia is liberated. Ammonia is liberated in that case. Ammonia is liberated. That is NH4Cl, when it is heated, it will form that ammonia plus HCl. That is how we get that on decomposition. And the B part is when the anions are, right, that is are ClO4 negative, right, that it is Cr2O7 2 negative, NO2 negative, NO3 negative, then we get or we can read that directly, NO3 negative, then we get N2 or N2O in the reaction. So let us check that how we can get N2 and N2O in the reaction. Suppose I'm writing like this. That is, we are going to write that it is NH4, that is NO3. Then in that case, I'm going to write that is N2O plus twice of H2O. And if I'm having that is ammonium nitrate, NO2. In that case, on heating, I'm going to get that is twice of H2O plus N2. And if I'm getting that ammonium, I write that ammonium dichromate, Cr2O7. Then in that case, on decomposition, we know that it will be N2 plus Cr2O3 plus twice of H2O. We'll get the product like this. So on decomposition of these, we are going to write the product as this in these cases. So these are the product in these cases. What will be formed in the reaction is. So we can write like this. We can say that how that ammonia is formed in the reaction is. So that is how we can discuss that ammonium nitrate is. So that is how the decompositions are. In these cases, we get that ammonium, that is N2O or N2 in the reactions are. So that is how we'll get the reaction is. So that is the thermal decomposition. Now we can write that other reactions which can be written for this is, that is the reaction of ammonia. We can write that as So we can write that the other reactions, whatever the reactions are, we can write like this. The other reaction of ammonia, whatever it is left, we can write like this, that is in other reactions. So if ammonia is treated with P2O5, so ammonia when it is reacted with P2O5 in presence of water, we are going to write that the product of the reaction is ammonium phosphate. I'm going to write that ammonium phosphate in the reaction is. So thrice, we can write that, this will be twice, we can get that is. So this is twice, we can get that is 6, we can get this, and then we can add water according to the requirement. Because this is 5, so we require this, we'll get the product of the reaction. Next I can write is, that is, when I react with ammonia with, we say that ammonia is treated with CaCl2, then no reaction. But if I react water with CaCl2, the reaction is like this. I can write that when water is treated with CaCl2, then the reaction is there. Both are Lewis bases, the water as well as ammonia. So we say that this is hydrated and this is hydrated, no doubt. So we are going to take this as hydrated CaCl2. Then we get that CaCl2.8H2 is formed in the reaction. But if it is anhydrous, there is no reaction. So if I write that it is anhydrous, then there is no reaction, like that. But if I say that the excess of ammonia, that is the ammonia that is hydrated CaCl2, that is hydrated, and excess of ammonia is used, then we get that NH3 whole 6, and then we can write that the CaCl2, that is how we get that the product is. Then in that case we get a complex. So that is how the reaction is. The other reaction of ammonia is, we can write that when ammonia reacts with NH3 reacts with Cl2. If NH3 reacts with Cl2 and this is an excess, because there are two type of reaction, it shows one when this is an excess, other when Cl2 is an excess. When we say that the NH3 is an excess, then in that case we used to write that it is going to form when right now NH4Cl and N2. So this gives NH4Cl plus N2 is liberated. But when this is there, then we used to write that, then in that case NCl3 is formed plus HCl is formed in the reaction. So if this is an excess, we get NCl3. If this is an excess, we get that ammonium chloride. So we get the reaction like that. NCl3 plus, that is, we get that NCl3 plus Cl2, that is HCl. You can write the thrice of this. So you can use that thrice of HCl. But in this case, when ammonia is an excess, we get 6 times of this and we get N2 in that case. So for that, I'm going to write that it is like this. So NH4Cl and we get the reaction like this. So in that case, we get that the product of the reaction like this, that is we required is. So, but here it is 6, so N2, so 8. We get that the balance reactions is, yes. So like that we are able to write that the reaction is, we can write that the other reactions of ammonia with that is when it is treated with Br2, we get like this. So when NH3 instead of Cl2 we are going to get Br2, then it will form that 6NH4Br plus N2 is liberated. The reaction is very similar with Br2. So NH4Br and we get that N2 gas is liberated. And this NH3 with I2, if I treat that NH3 with I2, then it is going to form that is NH3.Ni3, that is an explosive compound which is formed in the reaction is. So Ni3, that is explosive compound, plus thrice of Hi is formed in the reaction, plus thrice of Hi, what we get, you can balance that. We require twice of nitrogen, N3, that is thrice of H2. We get like this. It is an explosive compound which is formed in the reaction. So at room temperature, it is an explosive compound which is formed in the reaction. So I'll write that it will explode and gives like this, NH3.Ni3, it will explode to give. Then it will explode to give the N2, I2 and NH4I. So we get that N2 plus I2 plus NH4I in the reaction. That will explode to give that a reaction is. So you can write that it is 5N2 and we can write that it is 16. So we get that 6 of this and we get that the 9, you can write that 9I2. So like that we get the reaction is. So that is how we are able to write the reaction of Cl2 and Br2. It is almost same, but depending on that excess nature we get NCl3, but here we get that NBr3. Even if you take in excess you get that NBr3 in this case also. This is an excess what we are writing here. This is an excess. And if we take I2, then in that case we get that the explosive compound, that is NH3. Ni3 is formed, then it get exploded and converted into the N2 gas. So that is the intermediate compound which is formed in the reaction is. So that is how the properties of ammonia is, and that is all what we required for the ammonia compound is. So that's all about the ammonia what we required is. In the next class we can discuss about that is the nitric acid. So that's all about the ammonia is.